Okay, welcome back this morning to Back to Deflection. ME3228. This is YouTube video lecture number 3, whiteboard number 5. Okay? And so this morning what I want to go over a little bit are some of the parameters, properties, and a sample problem regarding deflection, and then also wanted to interject a little thing about beam design and section modulus. So let's get started. We're going to examine a typical deflection formula that again have been derived from some of the other methods such as moment area, superposition, or successive integration perhaps. But these formulas have been derived for standard types of beam sections that we've already discussed that are all reside inside this particular AISC steel construction manual or other resources for you. And we have chosen just a basic standard beam, simple beam, concentrated load at center. And I've drawn, as I told you in the very beginning, there are 4 diagrams that you normally look at a beam with respect to some kind of a load on it. And so this is the load diagram here, a shear diagram, moment diagram, and then a deflection curve down here, as best as I could draw it. So here we have a simple beam, concentrated load in the center, as noted by P, and then we have L being the total length of that beam, and then of course P is at midspan, so this would be L over 2 and L over 2 here. Now, as far as the shear goes, that's just the standard shear diagram for that type of a beam. The shear basically is going to equal to the reaction at each end, which essentially is going to be 1/2 of P. So we go down here to the moment diagram, and the moment diagram, of course, is equal to area in the shear diagram, but the way to put that with respect to these terms, the maximum moment will be 1/2 P times L over 2. This is 1/2 P over L over 2 here, which essentially breaks down to PL over 4. For the maximum bending moment, which you'd use in the bending stress formula or the flexural stress formula. And as far as the deflection curve goes, we know that it's going to kind of look like this, a negative deflection here with the maximum being at center span here, Y max. And again, according to the formula method and that particular beam type, it is PL cubed over 48 EI. Okay, so let's look at just a sample problem real quickly. And we're going to determine the maximum deflection for a steel W4x13 beam. Now, let me tell you a little bit about what this W4x13 beam is essentially. This W14 4x13 basically means, you might call it a I-beam, all right, but the technical term nowadays is W, which stands for wide flange. And of course, the top portion, bottom portion would be the flanges, and the vertical portion is called the web. And a W4x13 means that essentially the basic depth of this would be only 4 inches. All right, and then the 13 stands for the weight per foot. So it would be 13 pounds per foot and a 4-inch deep beam, essentially. Okay, so that beam is 10 feet long with a concentrated load of 2,500 pounds, or 2.5 kips, at midspan. Okay, now for this particular design, they have a Y max allowable, which needs to be less than 3/8 of an inch, or 0.375. So I've drawn the little beam down here. Here it is, 2,500 pounds, midspan, 5 feet on either side, and that being the W4x13 beam. Now, there are two variables, and we're going to talk about those variables here in a moment in detail. But overall speaking, these two variables here within a deflection calculation, and they are I and E. I and E. So we get the I. We can use an I if it's just a standard shape or a composite shape. We can calculate what that I is. But for standard structural shapes, of course, we would go back to the reference section, the shapes and properties of these various shapes, and this is what this would look like. This is a W shape. On one side are all the dimensions, specific dimensions, and on the other side are the properties of those W shapes. And this is the smallest W shape you can purchase out of the mill, which is a 14 by 13. Here are all the dimensions to it. But more importantly, over on this side, what we're looking for is the I. And here is the I right here. Of course, we're going to be using about the XX axis, which is the standard axis. And and you look and see it's 11.3. And that's inches to the fourth, 11.3. That's where we got the I from. Okay. And of course, we would just have to know steel, and steel basically ranges anywhere, depending on who you talk to, anywhere from 29 times 10 to the 6 psi. Some people just call it, round it up to 30 or 30 million psi. Be that as it may, these are the two variables within this equation that we know based upon what it is and what the shapes are. So this is what we do. So then we just plug this in, and P, of course, is 2,500 pounds. L is the overall length. Now that's 10 feet, but of course we have to keep our units straight as usual and compatible. And so this would be 10 feet times 12 inches cubed over 48, which is just a constant here, times E, which is 29 times 10 to the 6 pounds per square inch. Here we got inches to inches. And then times the I, which is 11.3 inches to the fourth. Okay. So at any rate, once you do all the arithmetic there, it breaks down to 0.274 or 274 thousandths of an inch, which is just a little bit over 1/4 of an inch at 250 thousandths. Now, what that tells us also is that we had an allowable of 0.375, which obviously is below that 0.375. Therefore, this particular shape with this particular material, steel, would work for this application, for this design, whatever that might be. It might be a frame on something, a trailer, or whatever it might be, or a machine loaded this way. So at any rate, this would definitely work under those circumstances. Now, let's remove this board and let's look at something. Let's look at some more with respect to the parameters, all right, and properties here. And what I want to do is break this thing down for you a little bit. And I'm going to do that by looking at, let's look at the variables within the equation. And again, if we go back to that equation of, and for that beam it was PL cubed over 48EI. Now, what I want to look at specifically is the E and I, because the E and I are the variables. It's something that you can change, okay? And as a designer, as the engineer, normally you can't change, the given. Make sure this is all. Whoops. Whoa. Yeah. Okay. So normally we can't change the loading situation, but we have the other things to change. So let's look at these E and I. Now, from a material standpoint, this E and I, or actually these E and I, the E, as we said the other day, E, the product of E and I is represented as the overall beam stiffness factor. And we said that deflection is inversely proportional to this beam stiffness factor, which means it's always in the denominator. So the deflection is always inversely proportional to this beam stiffness factor, which is E and I. Now, E, of course, is a stiffness factor based upon material. And the I is also a stiffness factor, but it's based upon cross-sectional geometry orientation. That was that XX and YY axes. Okay, so this is what we can change, of course, as engineers. And so we have I being stiffness factor for the shape geometry, and E being the materials stiffness factor that we look at. So let's look at E, for instance. E, of course, is just the modulus of elasticity. Okay, and we know that, of course, to be equal to stress over strain. And if you break the variables down, of course, you can get F over A over little delta over L. Okay. Now, these values for E's, each material has an E. And we get those, of course, we get them through experimentation by using the tensile test, which you'll get to use later on. But as you can see here on this basic table of material properties, here is the modulus elasticity E, and this is kips per square inch. But there is steel at 30,000. You may not be able to read that, but this is 30,000. You come down here to stainless steel is a little bit less. Again, about the same, 29,000. Cast iron a lot less at 15. Now look at aluminum. Here's aluminum at only 10. All right, titanium up at 16.5. Let's see, copper 15,000. So at any rate, these are the values of E that you can obviously look up, but these values have been achieved based upon this equation, that this data has been obtained from a universal standard tensile test, which you'd be able to do. All right. Now, as far as I goes, I, of course, is the moment of inertia. Moment of inertia. All right. And it is, again, a cross-sectional geometry orientation value along those either X or XX or YY axis. And it is obtainable through standard structural shape tables, which again would be in that AISC manual that I just got through showing you a moment ago, as this clearly depicted here. So all of these I's are here on XX axis and YY axis. All right. Now, so this is where you obtain these. Now you can get these, of course, for, like I said, wide flange beams, channels, angles, pipe, tubing, rectangular tubing, square tubing, etc., etc. They're all inside that manual. All right, and the I's are very obtainable very easily just by looking this thing up. Of course, if you're working with a composite shape, two rectangles or a T shape or something out of specific material, then you'd have to calculate that. All right, which is fairly simple to do. Okay, for instance, for a standard rectangle based upon this orientation, the I would just equal BH cubed over 12. Okay, for that orientation. Now, if you turn it over around, then you still use this, but then the base and the heights change, and you can see, its stiffest orientation is the vertical going this dimension vertically. This is a 2x6. This would be 6 inches. So you can see laying down the other way would be much weaker. The values would decrease. So These we're looking at maximum values, maximum values. The greater the value, the more resistance to bending, or the greater the stiffness is. Okay. All right. So now let me interject one other thing here that I want to talk to you about, and that's in the field of beam design using this criteria. If I have something to wipe this off with real quickly. Let's talk about a term you may not be familiar with, but let's see if we can get through this. This is based on the Flexure Formula, which is basically bending stress. Now, you know that equation to equal MC over I, and there's that I, okay? Now, what I want to introduce you to is a term called the section modulus, okay? So, if we were to look at this, and we try to put these terms in a little bit different scenario, if we put I over here, if we rearrange this to look something like this, I over C is going to equal to M over sigma max. Okay, so now we have that equation in this term. All right, now this is what I want to highlight. See this term right here? This term I over C is something referred to as the section modulus, and the term is S. All right. Now notice that this is all based upon the geometric dimensions on that specific cross-sectional shape. The section modulus is. So this is it's all in inches, and so this is going to end up to be inches cubed. But be that as it may, so this section modulus, then if you write this in as S, then this becomes S is equal to M over sigma max. Okay. Now I'm here to tell you that in most elastic designs for beams, when you go about looking to find the right size beam, this is the quantity you will be looking for. Okay, and so basically what you'd be looking for is S required, and because you're going to know the maximum moment, you're going to know the stress, the maximum stress that component is going to be feeling based upon bending. Calculate that, and then you just go and find an S that would be either equal to or greater than this particular value. Okay, there goes the timer. So this S required will be the basis for choosing beam size based upon maximum maximum bending tensile strength. Okay, and so this obviously would be attainable based upon what kind of material you're talking about, steel, aluminum, what have you. So it's just something that I want to make sure you understand on beam design from this standpoint, that we look at that this quantity I over C is referencing the section modulus. And I tell you, if you go back to this table, if you look right next to the eyes, on these tables, there is the S. Okay, there is the S, and so maybe I can blow that up for you a little bit here. Okay. All right. So here is the elastic properties. Here's the I, here's the S. Okay? So in other words, if you found a beam based upon the steel sigma max and its maximum moment that you calculated based on a shear moment diagram, and plug that in, all right, you're going to get an S required. And then all you have to do is come through here and look at all these different shapes. Again, wide flange, channels, angles, rectangular, whatever, and start looking for values in excess of that required S value, and then you would choose that beam. All right, you would choose that beam based on these values. Okay. Okay, so just a little heads up on beam design predicated on elastic properties. How you'd go about doing that and solving for an S required. Okay. All right, so we will finish this. This was I believe number 6 whiteboard lecture here, but actually video number 3. So we are completely through with deflection, and I'll be in contact with you vis-a-vis email as far as when this first little quiz is going to be available for you. Okay? We will talk to you then.